Dependent versus independent variables. Let's have a look at an illustration. Suppose we want to know what the relationship is between corporate sales and GDP growth. In this instance, corporate sales growth would be the dependent variable and GDP growth would be the independent variable. In other words, corporate sales is dependent upon what's happening in the broader economy. Now, to estimate this relationship between corporate sales and GDP, what we're going to do is we're going to look at some historical data from some sample period. So, for example, the analyst may look at the monthly data over the last 5 years. So this would represent 60 observations. Now, using these 60 observations, the analyst would then regress the sales data on the GDP data. And here's a visual depiction of what's going on here. So here's sales, the dependent variable, and here's GDP, that's the independent variable. And each red dot here represents an actual observation. So I know in our example, we're saying we're going to use 60 monthly observations, but just for simplicity, we're just going to have 4 observations here. It'll be the same if you had 60. Now, each dot tells you what sales and GDP were for a particular month. So for example, if we focus in on this dot right here, or that observation, this tells you for that particular month, sales was here while GDP was there. So each dot is telling you what's happening between sales and GDP. But of course, the more dots or more observations we have, the clearer the picture that emerges between the relation between sales and GDP. So once we have all these observations plotted out, the next task is to draw a line that best fits through the data. And that's what that blue line there is. So that's your regression line. It's the line of best fit. So what we want to do then is we want to come up with a framework or an equation that represents that line. And really, we're going to be using this regression to estimate, and that's what these hats mean, to estimate what the value of y would be when we're forecasting a particular value for x. In other words, if we assume a particular value for GDP, based on this framework, what might be our estimate for sales growth? So to do that, we just use the same framework for the equation of a linear line. So we need the intercept term, so that would be B0 right there. But note again that we're using these hats here. And here's why, ladies and gentlemen. Here's why. Because regression only estimates the relationship between sales and GDP. Why is that? Because look at where we got this regression line from. We only used 5 years worth of data. So basically, we're using a sample observations to express the relationship between sales and GDP. The fact is, we don't know what the exact relationship is between sales and GDP. For example, if I tell you what GDP is going to be next year, there's no way someone can tell me precisely what sales will be next year. The best we can do is just form an estimate having used historical observations. So that's the storyline that goes behind this regression analysis. So again, let's go back to constructing the equation of that regression line. So we start with B0, or I should say an estimate of that intercept term, because remember, this is just based on a sample. Then we go up a slope, and the slope is measured by beta 1. And then, so let's just suppose we're trying to plot that number. And so you're going up a slope, and then you stop where you get to the value for GDP. In this case, it's the independent variable, and there it is. Now, the regression represents the average relationship between sales and GDP. It's not always going to give you the exact number. As you can see here, when you draw a line of best fit, what you're going to get is errors. So see that? That's an error. That's an error, right? Because the regression line does not cut through it. In other words, the actual observation was something different. So for example, if we're looking at this x value, the regression would estimate that y would be right here, but the actual observation is right there. So that's why we refer to these as errors. And you can see another error there, and you can see another error there. But here's the thing, ladies and gentlemen. Here's the thing. Some of those errors are above the line, some of those errors are below the regression line. So when you average out those errors, their expected value is 0. So yes, there will be errors because the regression is simply a line of best fit, not an exact fit, but best fit. So of course you're going to get actual observations that deviate from the regression line. But on average, those errors are expected to be 0. So there it is, ladies and gentlemen. This here is your regression equation, which is the exact same thing as the equation of a linear line, which I think we all learned back in grade 7. That's all it is. All right, so let's continue. Suppose that the regression estimate is as follows. So sales is equal to 2 plus 0.6 times GDP. And again, we're just using this regression framework here. So this would be the estimate for the dependent. This is the intercept term. That's the slope coefficient. And this, of course, is the independent variable. So what observations can we make here? Or what conclusions can we draw? As I said before, the actual relation between sales and GDP is unknown. For instance, if you're given GDP growth for next year, we would not know exactly what sales growth will be. All we can do is form an estimate. And again, that explains the hat, right? It says this is our estimate. I don't know exactly what sales will be next year, but here's my estimate based on historic observations. And how are you going to form this estimate for sales next year? I'm going to use my regression equation, which I derived from historical observations. Now, how do you interpret the coefficients? The coefficients are the betas, or the b's, I should say. So these are your coefficients right there. Well, we said assume that B0 is 2 and B1 is 0.6. So let's interpret that. So what does B0 equal to indicate? If GDP was to equal to 0, sales would be 2%. So let's see if that checks out. So if GDP, if this was 0, what would happen? So 0.6 times 0, it'd be 0. So therefore, sales growth would only be 2%. So therefore, B0 represents the effects of all factors other than GDP. So let's go back to this framework and see what that means. Ladies and gentlemen, here's sales, right? Now, corporate sales is affected by a lot of factors. For example, it's affected by things like consumer income, exports, imports, exchange rates, interest rates, inflation. But you only have one factor, right? So do you see how this works? So GDP only explains this portion. Well, what about all those other factors that affect sales, right? Remember we were talking about like consumer income? Where's that? You got it. It's right here. So anything not captured by GDP, or I should say any factor affecting sales other than GDP would be captured in that intercept term. And that's exactly the point we're making here. Well, how about this B1 0.6? This would indicate that for every 1% increase in GDP, sales will increase by 0.6%. So let's go check it out. And again, ladies and gentlemen, this is just nothing more than elementary algebra, right? So if this goes up by 1%, even if you don't know anything about sales and GDP, and actually even if you don't know anything about quads, it's right there. If this goes up by 1%, 1% times 0.6, therefore collectively, sales would go up by 0.6%. So as we indicate, B1 represents the sensitivity of sales to GDP. And that's exactly the point we make here. It's the sensitivity of sales to GDP. Now, how do we estimate the coefficients? Right? Like in my example, I just said suppose. So I just gave you these values out of thin air. But as an analyst, you would need to compute those estimates. So here's where we again have a look at the big picture before we dive into the computations, right? Where are you going to get these numbers from? Bingo, your sample. In other words, your monthly observations over the last 5 years. So that's what the data is used for, to estimate the coefficients. So what are the values for B0? What are the values for B1? That comes from the data. So the first coefficient we calculate is actually the slope coefficient, so it's beta 1. And that's your beta. It's just called beta. And the way it's found is it's the covariance between x and y, so the co-movement between x and y, divided by the variance of the independent variable. And again, what this is doing, you could see it's trying to capture the sensitivity between x and y, but it's scaling it. It's saying, what is that co-movement relative to the total variance of x? Now, once after you find B1, then you can find B0. And I'm going to show you the ground-up approach. So here's our regression estimate. That's the same one we saw previously. And here's an interesting property. When x is at its mean, y will be at its mean as well. So that's a property of constructing a regression. And I'll just take you to my original graph here just for a second, and I'll show you what I mean. By design, so this is not a coincidence or anything, by design, let's just say that the average value for x was here. So if this was the average value for x, here's what the regression property would be. Then that point would be the average value for y. And that's what we mean. So when x is at its average, y will be at its average at that point in time. So if that's the case, I'm just going to substitute that individual y with the mean of y. So basically I'm saying that, well, what if y is at its mean? Then we automatically know that at that point, at that exact point, x is at its mean as well. And so we rearrange the framework over there. But you're trying to solve for B0, okay? B0 is right there, so just isolate it, and that's exactly what I did in that third step. So therefore, B0 is equal to the mean of y minus B1 times the mean of x. Okay. So again, ladies and gentlemen, try not to memorize this, because you're bound to get a plus or a minus mixed up, and that'll give you the wrong answer. Instead, just start from the ground floor, which is our original regression framework. Now, when the coefficients are calculated in this manner, the resulting regression first will best fit through the data, and two, result in the lowest errors, i.e. deviations from the regression estimate. So these two say the same thing, right? So if the line best fits through the data, that means those observations are close as possible to the regression, and therefore the errors would be minimized. Note 4. How do we analyze the regression results? We go in the following order when we're doing the analysis. The first question we ask is the regression model valid? So if the errors are picking up a pattern, then the model is not capturing something important, and therefore it's not valid. So I'm going to play a little word association here. Valid, you look straight to the errors. So if you want to see if a model is valid, you look and see how the errors are behaving. Now, with a good model, with a valid model, the errors are supposed to be random. But if the errors are picking up a pattern, it means your model is missing something. And here's the framework. So here's the actual observation for y. And this is the regression framework that we saw previously. And then here's the errors. Now, if the regression model is constructed properly, what can you tell me about the errors? Remember, we said the expected value would be 0, and at the same time there would be random. That's what we said. So on the other hand, if the errors are picking up a pattern, so remember, y is either explained by the regression or the errors. So the first place you look at is the errors. So if the error is picking up a pattern, then you say the regression is missing something. Do you see how easy it was? So you don't actually dive into the regression. You don't even look at the equation. You look at the errors. And you say, well, if this is, again, if the error is picking up something, the model is not picking up something important, so I'm not even going to look at the model. So there it is. Any variation in y that's not captured by the regression will be reflected in the error. The second thing is, so after you determine that the model is valid, then you ask yourself, is the model significant? So there are two different things. Part 1 says, is it valid? Part 2 says, is it significant? What does that mean? So, and you got to go in stages. So when you're in stage 2 here, you're assuming the model is valid, i.e. the expected value of the errors is 0 and the errors are random. So once you've satisfied that condition, that's when you say, well, how good is this model? So do you see how it just flows? Once you say the error is okay, then you look at the regression and start kicking the tires, if you will. So what does it mean when we're asking ourselves, is the model significant? In other words, does the model explain a significant portion of the variation in y? That's the whole point of these models, is we want the model to do a good job of forecasting what the dependent value will be. So I've got two different scenarios here. So here's our first scenario, here's our second scenario. And you can see that it's the same regression line. It's the same exact blue line in both cases. But in the first instance, look how close the regression is coming to the actual observations. In other words, the regression is doing a pretty good job of trying to explain the actual values. But here, wow, look how far the regression estimate is from the actual values. So what's the conclusion? In the first scenario, this one here, the relation is significant because the estimates, as represented by the regression line, are coming in close, whereas in the second scenario, the relation is insignificant because these estimates are far off. And here's the thing, ladies and gentlemen, here's the thing. Just because a model is valid, so in both cases, remember what I said, if you're in stage 2, that indicates that both models are valid. But that doesn't mean you're going to start using it to make forecasts. For example, I will use this model to make forecasts because it's proven itself to come pretty close. But the second one over here, well, just because it's valid doesn't mean it's good at forecasting. In fact, this is making a lot of errors, right? So it's insignificant. So I am not going to use that model because it's not significant. It's not doing a good job of explaining what's happening to the actual values. And 3, once the model is deemed to be valid and significant, then it may be used to make forecasts.